I guess I'm Walter Bright, and this is about the D programming language. And, this, being a rather short presentation, so it'll just be kind of a taste of what's in there. It's a rich language. There's a lot in there. It's statically typed and natively compiled. So I hope that sets the stage. And, this last 3 days, things have been entirely too nice around here, so I'm hoping we can kind of raise the voltage a bit. Okay. This is the question I always get asked about D. The first thing they ask me is, why? Why a new language? I've got C++, I've got C, I've got Ruby, I've got Java, I've got Scala. Why would I be interested in D? Why would I want D? What niche does it fill? So that's what I'm going to try to answer here. Okay, the first thing is existing languages, modeling power. A lot of languages, the only model they give you is a brick. Okay, it's a one-note language. They decide they want that this kind of model works for everything, and they give you that nice, neat little brick. And it's great for making walls out of bricks. Bricks are perfect for building walls with. And so everything is fine. And you go on until, you try to model an airplane out of bricks, and it takes a lot of imagination and a lot of work to imagine or think of that as being an airplane. And it doesn't fly, yeah. You can't build a flying airplane out of bricks. You can't model one out of bricks either, or it looks pretty horrible. So that's the first dragon we want to slay, is we want better modeling power. Okay, the next problem is obsolete technology. Established languages tend to be older languages, and being older languages, they tend to be, there have been a lot of new ideas in programming languages, and the old ideas get obsolete. So how many of you have found yourself pulling the cannon through the mud with your programming language? Okay. It's hard not to look at that and think, if only my cannon had a motor on it so it could move under its own power, had some tracks on it so it could get through the mud, had a turret so I don't have to move the whole thing around to point my cannon, and maybe a bit of armor plating so I don't get shot while I'm trying to aim my cannon, and, a tank, basically. So if you got tanks, why are you stuck with pulling your cannon through the mud? This is actually from Flanders Fields in World War I, in case you're wondering where I got this picture. Okay, and the next thing is using your language and your weighting. You're waiting. And what do you do when you're waiting? What do you do when you're waiting for your program to load, your program to run? You do tweets? Reddit? That's what I do. That's why, people see me around on Reddit a lot, is, waiting. Funny thing is, something about D. So, yeah, they got the wrong logo. I think Reddit is the greatest time waster ever invented, because once you start looking at Reddit, then you want to finish what you're doing on Reddit before you go back and check and see if your program is getting anywhere on you. So waiting is another dragon that we want to slay. So what about existing languages? I know what you're thinking. All of these solutions or languages have solutions, but you usually only get about two out of three. You get modeling power, you get convenience, or you get efficiency. pick 2 out of 3. Well, with D, I want to show that what you get is 3 out of 3. That's the point of D. That's why we're doing it. We want it all. We want 3 out of 3. All in one language. We want modeling power, we want modern convenience, and we want it to scream. We want it fast, we want it efficient. We don't want to hold anything back. Oops. So, we're fortunate that the biggest D booster is President Obama, who's actually said, you want to go forward, you put it in D. He's our #1 D user. Okay, D has the modeling power. Remember those bricks? Well, MegaBlocks makes a bunch of other little modeling things, and by putting them all together, you can create a model that looks a heck of a lot more like an airplane. And this is a real model, and I know because my son has this model. That's why I thought of it. It's a great model, and it's you can do a lot more than you can with bricks. Okay, so I know I've been a little hard on this, but the right modeling paradigm for the job. And that means that you got to have multiple paradigms in the language, and you got to support them nicely, and you got to support them easily so that you can pick the right tool for the job without having to learn a whole new language or create a hybrid project or something like that. So here's 6 of the models that D supports. Polymorphism, object-oriented programming, basically. Value semantics, functional programming is the cure-all du jour. Generic programming is the cure-all 1998. Generative programming and contract programming. And I'll give you a brief taste of what each of these mean with D. So let's start with polymorphism. Everybody knows what polymorphism is. This is old hat. What D supports is single inheritance with multiple interfaces. And you might recognize it as the Java model. And it's very successful at what it does. And although nobody anymore claims that object-oriented programming is a solution to all problems, it is a solution to a lot of problems and is the most appropriate model for a number of issues. And D supports it, the standard model, very well in the usual way. Oh, I thought I fixed that. That's the problem with editing your slides at the last minute. Yeah. Well, there are some interesting things around here. Although interface is sort of like, Java and C#, the colon comes from C++ and not the extends thing. Constructors are done by naming them this instead of duplicating the class name. Then you have your parameters, and this all looks pretty familiar. And D's version of printf is called writeflen, where you give your string, and here's where the arguments go. And you notice they're all %s. Pretty much arguments know how to print themselves. It's a type-safe printf. And it's not built into the language. It's done with metaprogramming and templates and all those other modeling things. So this is not compiler magic. It's part of the language. So in addition to the object-oriented version of programming, where pretty much everything is a reference, D also has value semantics, because sometimes you actually want values, not reference semantics. And it does the usual. It's got a value type is distinguished as being called a struct instead of a class. And you can do construction. This is the constructor, as we saw before. This is a destructor, which implies RAII programming. Resource acquisition is initialization. I think I got that right. So it supports that model, and this is interesting. What's this? In C++, you have what's called a copy constructor. In D, what you have is called a postblit, because the D model of copying a value object is to do a memcopy, or a bitblit, and that suffices for nearly everything except for a few things where you want to tweak something after you copy it. And so anybody got an idea of what would be something you want to tweak after you copy it? Anything newable? A reference? No, in a garbage collected language, you don't need to copy what the reference is pointing to. Internal pointers? There you go, sir. Reference counting. You want to bump the reference count when you make a copy. That's actually probably one of the biggest. I have a hard time even thinking really of many other uses for doing something other than a blit. Okay, here's Haskell and D. That's for Bartosz. Functional programming consists of pretty much three basic things from my understanding of it. The first is data immutability. You got to have data that is guaranteed to never change. What you get with data immutability is, for example, is you can pass it between threads without any synchronization. Because all the synchronization problems come in when you have mutable data, not when you have immutable data. So you can type data. This is not a storage class. It's a type constructor, meaning you're actually creating an array of immutable ints and initializing it with 1, 2, 4, and 6. And after it's built, it is guaranteed to never change, and it's implicitly shareable between threads. Next thing you've got as a functional feature are pure functions. And that's a part of the type. It's a type constructor on the function type, and you just put pure in front of it. And so what does pure actually guarantee in D? Is there anybody got an educated guess? How does pure change the semantics of that function? No side effects? Close. Yes, sir. No side effects on free variables. Very close. What pure guarantees is no reading or writing of global state. Now, why do I make that distinction? It turns out that you can pass a pointer or a reference through the parameter, and it can modify through that view, but it can't set a global variable. And the interesting thing is, if you then tag your parameters with being immutable, then the pure function is guaranteed that it can't change those either. So it becomes what we call a strongly pure function. It can't change anything but give a value back. Yes, sir. Yes, you can modify global state through a reference, but you can't do it out the side. Yeah. And what that's guaranteeing is that function is not like squirreling away a copy of your data, for example, in some global table or something like that. So the next functional thing are lambda functions, and Herb asked me, does D have lambda functions? And there it is. And the interesting, yes, sir.
So I have a question. Can the pure function allocate memory? And can it modify allocated memory?
Yes, a pure function can modify its own local variables, number one. And number two, it can allocate memory. And we thought about, doesn't allocating memory change global state? And technically it does, but semantically, It actually really doesn't, because we've looked at a lot of, I've been programming for a long time, and I've almost never found a program that was successfully able to recover from out of memory. They either exit with an error message or they crash. And if you want to experience the latter, just try using up all your memory in Linux or Windows or something like that, and it usually starts behaving very badly, the operating system. So with that, we just made an executive decision that if operator new fails to allocate memory, it's an unrecoverable error, and your program exits. Yes, sir.
Can I not use this trick to, allocate a certain amount of memory and then later look at the amount of memory I've consumed in my pure function and therefore like store information away somewhere globally?
No, you cannot do that. It's actually statically checked. You can only call other pure functions, and it won't let you get at anything that isn't passed in through its parameters, that is, immutable state. And yes, it's possible there may be a crack in there somewhere, but when we find them, we block them off.
So your entire primitive library and things like this is all tagged as pure?
The pure was a relatively late addition to D, and so we've been going through the library and tagging things as the ones that can be pure as pure.
Is printf pure?
What?
Printf?
Printf is not pure and cannot be pure. It does I/O. It modifies global state. But you bring up an excellent point. How do you do a printf inside your pure function? Because D doesn't have monads. Oops. We agonized about this for a long time because, when you got this deep hierarchy of pure functions, down at the bottom you want to do a printf because you like using printf for debugging or something like that. And so D allows a little bit of an escape from purity. And that escape is, if you mark it as a debug statement, it will let you do something impure, with the convention that you don't release code that has any debug statements turned on. So debug statements are a language feature, and they can be turned on and off at compilation. So if you want to debug your pure code by putting I/O statements in it or loggers or things like that, yes, you can do it.
One of the invariants of programming talks is if you mention pure, you never get on from there. People will keep asking questions. So let's make this the last one.
One more question. Okay.
Okay. I want to know, is there not a need for an immutable array of immutable ints?
Okay. Arrays are by reference. So an immutable array of immutable ints, if you copy an immutable value, you can get a mutable value out of it. But the tail remains mutable. Okay, immutability in the type system is a transitive property. It turtles all the way down. But it works a bit like Lisp, where you can pull the head off, make the head mutable, and still point to the immutable tail. Does that make sense? So you can have a mutable array of immutable objects. So moving on, generics. This is a little piece of code that Andre wrote for the standard library in D. It computes the Levenshtein distance, and it returns the difference between the two ranges. And you're passing in a range. Who doesn't know what a range is? One person? Okay, in C++ you have iterators. An iterator is modeled after a C++ pointer. A range is the same idea, but the model is an array, not a pointer. So a range really is a fancy sort of a generalization of an array. So we're passing two arrays here expressed as ranges. We have they can be two different types. This A list equals, we can pass, this is the default comparator function. So here we're specifying a default lambda for it, and we put constraints on our parameters saying we want them to be forward ranges, or both of them to be forward ranges as opposed to forward and backward ranges or random access ranges. This little bit here are called template constraints, and they're actually a proposed feature for C++, whatever, the next version of it, C++ new. Yes, sir. Good question. Okay. Levenshtein distance is a function that happens to be a template. It's a template function. Size t is what it returns. This first set are the type parameters. Okay? So it has two sets of parameters. It has the types, and it has the values passed as arguments. And when you normally would just pass it t and s, and it will figure out, using type deduction, what range 2 and range 1 are, because those are the types. And an alias means, alias in D is another word for a symbol. So you can have an alias of any symbol in the language, and one of those symbols could be the name of a function. So we're using this to represent a function, and the equals here means it defaults to this. So if you don't supply it, it supplies this default function for you. Now you might ask, where are the types in this function? And if you use this form of function, D actually creates a template function for you and infers all the types. So it's completely type generic or parameterized on the types. No, the fact that you don't specify types here makes it generic. What makes Levenshtein distance generic is it has two parameter lists. The first one is the type parameters, and the second one are the value parameters. Is the if the beginning of the body of the method? The if is called the template constraint. So what it does is it tests the types coming in at compile time to make sure they meet some constraint. And is forward range returns is another template which returns a Boolean true or false, saying does it meet this criteria of this template. So are you familiar with concepts in C++? That's what this does. It's saying the actual function is the open curly brace, close curly brace with the ... Okay, good question. Why the bang instead of, let's say, in C++ and other languages you use angle brackets? The reason is because it's syntactically not ambiguous. You can parse the thing without having to do semantic analysis. That's why it's there. Okay, the next kind of programming is generative. And this is the Mandelbrot set, which is an example of generative art. So D does not have bit fields. But it turns out, and this was developed by Andre as well, is you can create a template called bit fields, of course, which you can pass in the types of your bit fields, the name of the fields as a string, how many bits they consume, and you give a list of these. And what this returns is a string, an actual string literal. It generates a string literal, and what the mix-in statement does is tells the compiler, take this string literal and insert it into the code at that point and compile it as if it was typed in there. And so then we can declare an object of type A, and we can use the bit fields just as we would in C. So this is an example of using generative programming to add a feature to the language that doesn't exist in the language. It is not a macro language. What this relies on is a feature in D called CTFE, which is compile time function execution. And what that is it's kind of a super constant folding. Any D code that doesn't have side effects can be executed at compile time, including code that parses and assembles strings. So this is actually parsed and assembled into a bunch of D declarations as string literals, and then return this. And what it actually does under the hood is creates a function called X, and puts the bit masking and shift operations in that function, which is what you'd do if you were doing bit fields manually. But it generates that all for you. And that's why it's called generating. It's actually generating D code, which is then compiled by the decompiler. It's a similar idea to template metaprogramming in C++, which you use to generate code, except this is actually generating D code at compile time. Yes, the neat thing about CTFE is you don't have to learn another language to do things at compile time. It's the same language. In fact, you can take the same function and run it at both compile time and at runtime, depending on the logic of your code. Yes, sir. Yep. Yep.
Can you repeat the question?
He said, can you recursively have mix-ins? Yes, you can. And if you fail to have some sort of termination in there, yes, you will cause the compiler to say, too many recursions.
Let's do one more question here and then move on.
Is bitfields a keyword in the language?
No, bitfields is a template, a user-defined, library-defined name. This is not part of the language. Okay, it also has contract programming. What contract programming is you can put assertions on a function entry and a function exit. And the entry functions are called the requires clause, and it's indicated by the in keyword. And you can use that to do runtime tests of your input parameters. And the contract forms part of the interface. So here I have an interface, which you saw earlier. And the interface must provide this function. And we can do runtime tests on the argument to verify that something is within range. Because, type systems have their limitations. You can type it as being an int, but you can't say anything about the contents of that int. So you can use contracts to do a runtime check and make sure that the int satisfies your constraints. And not shown here, but you can also do out contracts, which test the result of the function. So for an example, if you have a function that's doing a square, you can have your out thing take your inputs and multiply them together and verify that, yes, indeed, you're coming up with the square. Yes, sir. You put a parens and you put result, so you give it a name. Yeah, to shorten the slide, I didn't put that in there. So here we can implement the interface, and it will inherit the contract. And if we do a derived class from that, and we override, got to do override to. It doesn't have implicit overriding anymore. 10 minutes. Oh my God. I thought I had too few slides. Apparently, we've got way too many. Okay, this is contract programming. Let's just move on. What D also has, this is a computer-controlled milling machine. Instead of milling everything out by hand, you just sketch it out on a computer screen, and it will actually cut the part out for you, which is an amazing thing if you've ever seen one of these things in operation. So we'd like something like that in a programming language. And what we've got are things like associative arrays, static typing with inference, resource management, slices and ranges, immutability and sharing as type, system and safe code. Associative arrays, they work a lot like hash maps. except they're built into the language. Static typing with inference. Notice we have an array here of mixed types. And what D will do is figure out the type that encloses all of those, assign that there, and auto means infer the type. So here we're inferring the type. Auto also works on the return value of a function. We can infer the return type of the function. So we can get a completely generic min function that works on any type. Resource management, you can have automatic, which means garbage collection. You can do scope exit, which means do cleanup code when exiting the current scope, which I believe Andre is going to talk more about later on. You can use C++ style, which is RAII. The file here is closed at the scope's end automatically. Or you can do C style. You can call malloc and free. And yes, these really are the C functions. They're not fakes. They're not wrappers. They really are the C functions. Slices. Slices is, I believe, a D innovation. Let's say our file name is this string, and we can slice it, which is to take parts of the strings out, and it doesn't make copies. It's just simply under the hood manipulating pointers and lengths, pointers and sizes. So it turns out to be very efficient and very fast because you don't have to allocate memory to do things like break up a file name. You know, you don't have to have zero termination, which means you don't have to break up the strings. Ranges, as you said, was a generalization of arrays. And the range here is we can read the standard input by line. And it will feed the lines to this variable, which, and then this one computes the number of lines, add up the line lengths. And here we then, when we're done, compute the average line length. Okay, this one is kind of fun. It's I want to do some numerical integration. Integrate from x1 to x2, f of x dx. Here's my integrate function. I take two double arguments, and I take a delegate, which is a pointer to a function along with its context. And that corresponds to this f and this f. So I take the sum, and here we have the standard loop, which I've done 10,000 of those loops. I can do them in my sleep. It's like one keystroke for me. I can plot these things out, compute the sum, and I can drive it this way. Passing it our lambda, c times x squared, because I want to calculate a parabola and thing. So this is old style. What would new style look like? We make it a template so it works with any type instead of all those darn doubles everywhere. Auto, so it infers the return type. Auto, it infers the type of this. And here we've replaced the loop with reduce and iota. What iota does is acts as a generator and feeds new values into reduce, which takes our current sum and adds f of x times dx to it. So, and the neat thing about it is completely generic. I can replace the range that generates things. I can replace my reduce lambda function. And so I can get rid of a lot of the loops in my code and replace them with generic replaceable things that just snap together. That's the neat thing, is you can take all these components and just snap them together in different ways. Okay, Michael Bay was reviewing my presentation and said I needed some I needed some explosions, so gratuitous explosions, of course. Okay. Oops. Yeah. Yeah. It's a new feature, and I hear C++ new is adopting it. Explosions. We talked about this a bit before. Immutable as a type constructor. If you don't say immutable, your data is thread local. This is actually thread local data declaration. Or you can say your data is explicitly shared among multiple threads. You can divide up your code between guaranteed safe code versus trusted or system code. Safe code, by that I mean it's memory safe. no buffer overflows, no dangling pointers, no pointers to garbage. Okay, the next thing we've got is native efficiency. The last solution. This argument's been going on the whole conference, so I guess we don't need to continue with that. D has direct access to C, including malloc free and even alloc A. Let's allocate off of the stack. It has an inline assembler, so you can do like a check multiply. And for x86 inline assembler, you can do it this way, or you can do it the slow portable way, and throw an exception if it overflows. So to sum up, D combines modeling power, modern convenience, and native efficiency all wrapped up in one language. Can D go mainstream? Who is running D? D is run by a bunch of volunteers. We have no corporation behind us. We do it because we love it. Okay, we're not being paid to do it. We like doing it. We think it's a great language. So can D go mainstream against those big competitors funded by, large groups of people and stuff like that? And, well, what can we say? Certainty of death, very small chance of success. What are you waiting for? Okay, here's our website. Here's our forums. The forum is all powered by D, so you can see D in action. It runs the forums. If you want to contribute, all the code's up here on GitHub. And if you want to come talk to the D community, we're having a conference in September. So, questions? Sir?
What happens when the next great modeling idea comes along?
D will absorb it. Anders is already telling me about await and async, so, But actually, right now, we're focusing on the tool chain stuff like that, and we've kind of closed the door on more features for the time being anyway.
You said that associative arrays are part of the language. Why did you make this decision instead of just having a standard template library or something like this, where it's just part of the user code, basically?
So the question is, why isn't associative arrays part of the standard library? And the answer is because associative arrays got in the language long before it got template support in. Yes, sir.
I wasn't really following how the string generation from D code is not like a macro. So could you clarify a little what the difference is?
Well, a macro would be an external process with a defined language that substitutes arguments and stuff to build new strings. The string processing in D is whatever you write as string processing code. You can write whatever you want as long as the output is a string. So I don't think that really qualifies as being a macro language.
I'm curious about how the macro staging works. How does when do macros become available to the compiler?
It doesn't have macros.
Oh, I mean the the whatever you call it.
The mixins happen as it's line by line semantically processed. That's when they happen. So it happens in lexical order. So, more questions? Sir?
This is actually just why the choice of the name, particularly for that one, mixins, when that's kind of an overused term in other systems?
Well, we use static too. It seemed like a good keyword for it.
So I'm not going to dispute the name, but I am going to ask. So Martin was talking about a similar concept that he did call macros, but I'm fine with mixins. But how do you? Same question that somebody asked him. How do you debug them?
How do you debug mixins? That's an ongoing problem. Generally, how you debug mixins is you can put in a temporary print statement, which will a pragma which will print out the string you're generating. And so you can see what the string is, and then you can see why it's failing.
That seems to be it. Let's hurry while we are stabilized here. Thank you very much. That's great.
Thank you.
Thank you.